All right, ladies and gentlemen, welcome to another episode of Simpkins Physics Corner. Today, it's conservation of momentum in 2 dimensions. And what is this inelastic versus perfectly elastic versus perfectly inelastic equations? What's going on with that stuff? So let's take a look at a conservation of momentum problem. We have a small puck, that's this one, of mass 0.1 kilograms, is sliding to the right with an initial speed of 8 meters per second on an air table. An air table has many tiny holes through which air is blown. The resulting air cushion allows objects to slide with very little friction. The puck collides with a larger puck. So basically I just said there's not that much friction, or friction is negligible in this problem. The puck collides with a larger puck, mass of 0.4 kilograms. That is initially at rest. And this figure is the one it's referring to. Shows the outcome of the collision. And the puck moves off at angles, angle 1 60 degrees and angle 2 30 degrees below the initial direction of the motion of the small puck. What are the final speeds of the pucks, and is this an elastic or an inelastic collision? Alright, so the first thing we need to understand is one-dimensional versus two-dimensional momentum. In this case, you may ask yourself, well, at the beginning of the problem, this puck, the large puck, has 0 momentum. It has no momentum up or down because it's not moving up or down with a velocity in the vertical direction. And it doesn't have a velocity in the horizontal direction either. So it has no momentum. The small puck, puck M1, it does have a momentum in the x direction. I'll call it px. And that can be found simply by doing the mass times velocity. So 0.1 times 8 will get us 0.8 kilogram meters per second of momentum. So this can be said to be the total momentum before the collision. The total momentum before the collision is 0.8 kilogram meters per second. Now, that's all the momentum we have to work with. Initially, and I should say the total momentum in the x direction, but it also turns out to be the total momentum overall, because before the collision, there is no momentum in the y direction. The reason we can say that with certainty is that this puck is only moving horizontally, and this puck is not moving at all. So there's no vertical momentum at the beginning of the problem. So what we can do here is we can say the total momentum really is 0.8 kilogram meters per second. Now the added nuance of this problem is that afterwards, because this puck, as you can see, it kind of hits the very top edge, or not the very top edge, but certainly not the middle of the large puck. It hits the edge here, kind of glances off. And that's why this puck moves down and this puck moves up. But based on what we know about momentum, if there was no vertical momentum before the collision, then there should be a total vertical momentum of 0 after the collision. And if that's the case, which of course it needs to be, because otherwise we're defying the laws of physics, that means that the momentum of this guy, Py1, the momentum vertically of that one moving upwards, should be equal to the momentum Py2 of puck 2 moving down. They must cancel each other out. Just as if I were in a boat and I were to throw an object in one direction, my boat and I would move backwards in the other direction. So too, if this guy has a positive momentum in the vertical direction, this guy must have a negative momentum in the y direction to make up for that, if you will. Because we know that over on this side, after Py still has to add up to 0. You can't just create momentum. All right. Now, we also know that after the collision, our sigma Px must be equal to 0.8 kilogram meters per second. So the momenta of those two pucks added together must add up to that. So let's go ahead and start working into this one a little bit. We already know the total momentum before the collision in the x direction, and so that's going to be applying to these two pucks. All right, so that's really all it gives us. So the first thing we can do is find the y component of the velocities of these two guys. We know that P1y must equal P2y, and the reason we can say that for certain is because they must add up to 0. If two things add up to 0, they must be equal and opposite of each other. I'll even say P1y is equal to negative P2y, to be more accurate to say. Now, let's go ahead and consider our angles. This guy has an angle of angle 1, and so what we can do here is we can say, well, it has a certain upward momentum. We'll call this M1V Y1 equals M2V Y2. You can imagine this is going to get pretty crazy pretty fast. In fact, I'll probably need to move this sheet up a little bit so we can continue on. You guys have that have the beginning of the problem there at the top. So this must be true. All right, and we know the masses, so I'm not going to worry too much about that. And then, of course, in the x direction, let's go ahead and write an expression. I'm going to kind of call this all after the collision. In the x direction, we can say that this guy has some momentum and this guy has some x momentum. And so that's going to be P1x plus P2x equals 0.8 kilogram meters per second. M1 V1x plus M2 V2x equals 0.8 kilogram meters per second. All right, now we really have to be good at our vectors here because the velocities and the vectors are the things that are going to help us to work all of this out. Because we can write an expression up here for this velocity. This is the overall velocity. So what we can say is this V1, and since if we're looking for the x component of that, V1x would be equal to V1 cosine of this angle 1, and V1y would be equal to V1 sine of that angle 1. Also, for this second guy, V2x would be equal to V1 cosine of angle 2, and V2y would be equal to V2 cosine angle 2. Woo! That's a beast. Alright, so you can see how these guys are going to come in handy because we can plug them into here or here, and this is where we go from AP Physics to AP Substitution because we're just going to be substituting things all over the place. Alright, so you really can jump into this wherever you want, but the whole idea here is to get the overall velocity of this guy and the overall velocity of this guy. So we want to solve for some just V1 or V2 somewhere. Alright, so we can jump in really wherever. Since this equation looks a little simpler, I'm going to jump into that one, and we'll see where we get from there. Really, it's just a matter of solving for something here. So let's go ahead and break this one out a little bit. I'm practicing some pretty bad paper etiquette. Let's go over here. So we have M1, and we know that Vy1 can be written as V1 sine of angle 1 equals M2 Vy2. That would be M2 Vy2 can be expressed as V2 cosine of angle 2. Alright, and I'm just going to go ahead and solve that for V1. So V1 would be M2 V2 cosine of angle 2 over M1 sine of angle 1. That's ridiculous. But we're getting closer, I promise. Because what we can do now is we can shift over to the y direction, and here I'm going to derive an equation. Actually, what we do is we can just plug all of this right into this V1, because we now have an expression for V1. All right, so we have to be really careful about how we do this. So let's go through this with care. So here's the work for plugging in to get the answer here of 1.717. Round to 1.72 if you want. Whew, all that work for just the velocity of the second puck, V2. So if we go back to our problem here, it did ask us to solve for what are the final speeds of the pucks, plural, so we have one more puck to work on. All right, so I'm going to need a little more paper here because this one's getting a little crazy. All right, let me flip over here. Now the nice thing is, we know that V2 is equal to 1.717 meters per second, which makes our life a whole lot easier because we come all the way back to some of these equations we derived. We just want to look for a nice easy one. Oh, look, there's a nice easy one right there. So I'm going to start with that one. M1 Vy1 equals M2 Vy2. All right. And so if we go from here, all right, we know that M1 V sine of angle 1 equals M2 V sine of angle 2. And lo and behold, we have this V2 finally. So I'm going to solve for this V1. This V1 is equal to M2 V2 sine of angle 2 divided by, see over here, M1 sine of angle 1. And of course, now since we know this V2, our life gets a lot easier. So I'm going to come back in just a moment with the answer for this one. Well, hallelujah. We figured out the second velocity here is this guy. If you want to see the work for that, you can go ahead and check your work. Just a little bit of algebra from the equation we derived earlier. And so we find here that V2 is equal to 1.717 and V1 is equal to 3.97. Now the last part of this problem asks us, is the equation elastic? And an elastic equation is defined as, or a collision, excuse me, is one that is defined as if the kinetic energy before the collision, kinetic energy initial, equals the kinetic energy final. If the kinetic energy before equals the total kinetic energy after. Now before the collision happened, if we refer back to our problem, the only thing with kinetic energy was this puck, right? Because it's the only one moving. So before the collision happened, we had 1/2 m1 v1 initial squared equals, and then we have two objects moving afterwards, so there's two places we can find kinetic energy afterwards. m1 v1 final squared plus 1/2 m2 v2 final squared. So I'm going to plug in some numbers here and do the algebra, and we're going to find out if the kinetic energy before the collision is equal to the kinetic energy after the collision. And here's the proof or the check for if this is an elastic or an inelastic collision. If the kinetic energy before is equal to the kinetic energy after, it would be elastic. However, if we do the math, we find that we had a lot more kinetic energy before the collision than we did after the collision. And since kinetic energy is not conserved, we call this an inelastic collision, and this is the proof for why we call it an inelastic collision. Now, if you're asking yourself where did that energy go, it can come from some of the deformations of the shape during the interaction. It can go as sound, as heat, as different types of energies. It can be contributed to what we call an internal energy somewhere else in the system. But at the end of the day, this is called an inelastic because kinetic energy is not conserved. That was a beast, but we made it. Have fun.